In the last class I introduced CPU processor. Okay. So, some overview of processors, but now let us discuss some ways to speed up computation. So, there are very interesting ideas, some, well, in fact they are not very difficult ideas, even think, oh, I would have got it, that kind of ideas. So, one major way to speed up a code is vectorization. Okay. So, I can tell you an example. If you do a for loop in Python for array of, let us say, 4000 data points, 1D array, okay, 4000 data points. I will take some time, but if you do with vectorization, which I am going to, well, I will not run the Python code right now, but I will show you it is 20 times faster, okay, not 1 time, 2 times, it is 20 times faster. Okay. So, that happens via vectorization, and the idea is the following. So, this is the picture taken from this website. So, single operation is called a scalar operation. Okay. So, I may do operation like a plus b, two numbers a and b, two numbers, and it will write on variable c. So, this is called single scalar operation. A and b are numbers, okay, they are b are numbers, and c is also number. So, okay, I get one operation, maybe basically few nanoseconds. Okay. So, that is what I will get, but of course, it requires less number of registers, right. So, for A I need to store it in 8 bytes, B 8 bytes and C 8 bytes. However, the modern computers, modern CPUs are more bigger registers or bigger L1 cache, bigger register, well, in fact we need registers. Okay. So, what we can do is, instead of one number at a time, this operation is same, no. So, suppose I have an array, large array A and B, I want to add element by element. That means, I am adding AI plus BI equal to CI, and I ranges from 0 to 1023. Okay. Turns out we can take chunk of that array. So, you can take something like 16 of them and push it in the CPU within the processor. Within the processor, registers can accommodate 16 numbers, 16A, 16B, 16C, and so there are 16 of them, okay, 16 of them, 16 of these and 16 of these, and it can be done in one clock cycle, in one shot. So, here I have A, here I have B, and this is going to come to C. But imagine right now it is 8 of them right now, but there are modern CPUs are 16 of them. Okay, and we hope that you may get even bigger number of registers and you can do big operations. So, the idea is to put more memory inside the CPU, so that this can be done in one clock cycle very fast, and remember the clock speed is in gigahertz. So, this is happening basically in few milliseconds, a few nanoseconds. So, that is called vectorization. So, vector, no, I mean in physics we know, or mathematics we know what is a vector. So, instead of working with scalar or num1 number, you do it with a set of numbers, and this is called vectorization. And as I said, this speeds up array multiplication, array additions, or in fact many of these hardware are optimized to do A star B plus C. They can be done in one clock cycle, because the hardware is made that way. Okay. So, 3 arrays I can do this in one shot. So, this speeds up the code, and you should always avoid for loop in Python for arrays. You should try to do in this way, and it will speed up your code by 20 times. We will do this stuff in practice. So, I am going to show and time it, and you should see that how fast the code becomes. So, this is one schematic from a book by Rajaraman and Murthy. So, this is a vector register. So, we have these operations, no? So, you can see that load and store. So, this is a real implementation, and Cray was one of the first computers to employ this. So, Cray, in fact earlier number of registers were small, but Cray said, well, I will make a hardware which will have more specialized operations for computing for HPC. So, this is one such example. I mean, you can have your 2 multipliers, 2 adders, div and square root. So, this can do square root in 1 clock cycle. So, this will be complex circuit. Remember, we had this CISC, complex instruction set, and CISC can do this stuff in well, not maybe not 1 clock cycle, but maybe 2 clock cycle. Okay. So, this is called vector operations, which can do operate on a vector. Now, there is another way to speed up your code, but this is not for arrays. This is for speeding up your program. So, you written a program which is 10,000 line code, and I want to run it, speed it up. So, early computers would have, what do you expect? First instruction, I will finish it, then go to the second instruction, finish it, third instruction, finish it. But now that is not what is done. So, I will give you an example from industry. Okay. This used to be this is the Ford assembly line, 1913, more than 100 years back. So, you know what is assembly line? So, this is the tray, assembly line, okay, that will move, and each person will do something and the tray moves forward, and something else will be done by the next guy. Nowadays, this tailoring shop, normally people we buy all ready made clothes, right. So, why is it cheaper? Because there is one person who cuts the cloth, he is not very good in stitching, other person does the stitching, somebody does the finishing. So, in fact, they may stitching only this part of the cloth. So, you speed up the thing by moving the assembly line fast, and you have less, I mean, in 1 hour a labor can do much more work. Okay. So, that is how things are speeded up in industry, in most industries now. Okay. So, there is a nice video from a movie, Modern Times. In industry is assembly line manufacturing, but this is called pipelining, and in computer how do you do pipelining? Okay. So, clock 0, so this is clock cycle, okay, this clock cycle, and clock 0 is the before we start the machine, or before we not start the machine, but before start this operation. So, clock 0 we have 4 instructions, they are colored as green, purple, blue and red. Okay. I need to execute 4 instructions, and each instructions, okay, now I did not cover it, but if you look at any computer science book, so it has 4 operations. So, first the processor has to fetch the instruction, it will come from memory, it could be cache, well basically from cache it will come. Then decode the instruction. Decode means what I am supposed to do with it. So, instruction could be multiply number by 2 or take a square root. Okay. So, you need to decode it, then execute it, okay. And last is write back the data onto memory. So, each instruction has 4 basic operations. So, in computing this is how you divide the big task into smaller tasks, okay, and this has become standard. So, somebody will basically make circuits for fetching, circuits for decoding, circuits for executing, and circuits for writing back the data. Okay. There is specialized hardware which is doing it, and this just happens in clock, one tick 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 tick, this happens. Now, what do you expect? 4 instruction, if I do it one at a time, how much how many clock cycle I would take? 4 into 4, 16, right? No, 4 into 4, each of these stages are 1 clock cycle. You can't do fetch and decode in one shot. It comes, then decode, then execute, then write back. So, we expect 4 into 4, 16 clock cycles, but we can do in 8. How? So, first time you push in this green into the memory, into processor, sorry, fetch. So, this is a processor, okay, this processor, and this is in mem. Mem could be cache, okay. It is not coming directly from RAM, it is coming via cache. So, in first instruction green comes in 1 clock cycle. Well, I can't proceed to purple because purple may depend on what happens to green, okay. Instructions one happen after the other, right. I multiply a number by something, then add in the next cycle. So, I can't do all of them in one shot. So, they are different operations. So, green comes in, then I fetched already, okay. Next clock cycle, this clock cycle 1, next clock cycle green is decoded, green was already in. So, the decoder says, well, now I have the data, I can decode it, I have the instruction and decode it. But while this person is decoding, the fetch hardware can fetch the next instruction. So, my next instruction, this has come in, purple instruction has come in. So, I did 2 operations, fetching of some next instruction and decoding. Next clock cycle, whatever I have decoded I can execute now. So, this is executed, and whatever I have fetched, decoder circuit is free right now. So, that person can, the circuit can decode, and fetcher circuit can get a new instruction. So, blue has come, okay. So, this is pipelining, right. I mean, this is the assembly line is moving, okay. This is clock cycle 3 is done. 4th, now whatever I have executed I can send it to write back. So, this will be written back. So, in fact, next clock cycle it will appear in the RAM, but whatever I have decoded can be executed, I have fetched, I can decode it, and now new instruction has come in, okay. So, you can see this moving in clock cycle. So, it turns out we can finish this full 4 instruction in 8 clock cycles. I mean, this is there, I will share this slide with you, and you can see it turn 8. If I had huge number of instructions, it will be done in how many clock cycles? Let us say I have n instructions, n is large, n is 1000, then it will be 1000 plus 4. 4 is the overhead, this time these guys are all not doing anything. So, if a large n, then everybody would be working. Starting time, some people were not working, okay. So, that is made up. If n is large, it will just take order n cycles, okay. So, pipelining is implemented in all machines now, and they can perform in n operations. But there is one thing we should keep in mind, you should not use jumps. In a function, if you use if statement, then this pipelining is confused, because your data is, your instructions are all lined up, it suddenly says, well, I need new instruction, I am jumping somewhere, and that is where there is a loss. So, in HPC it is recommended that you write your code so that it does not have, well, it has minimal number of jumps, okay. You can use functions instead, do not use jump, use functions. So, functions will get a next block, different block, but should be running in blocks. Gotos are prohibited, in fact, goto you should never use. Fortran has goto, no, C does not have goto, it has been in fact prohibited. So, Python also I have not seen go to, and even if it was there I will not use it. Okay. So, do not use jumps, and the reason is quite clear here. Vectorization and this pipelining is speeding up our process. So, we can do this A star B plus C operation in concrete. I want to do this not well, this can be done by vectorized operation, but imagine that I do not have enough registers to vectorize it. Okay. So, I have this 5 data sets, I can vectorize it by pipelining. Okay. So, how do you do pipelining? So, get this these two numbers A 1 and B 1. So, in next segment I can multiply this A star B, and it is residing in register R 3, and then I get C 1 inside in R 4. So, these are registers R 1 R 2. So, first cycle A 1 and A 2 are kept in R 1 R 2. Next cycle multiply A 1 B 1 and fetch C 1. Then you go here and add. So, this is clock cycle 3, but meantime when I was multiplying I can fetch A 2 and B 2. I multiply A star B star, get C 2, and now in this cycle my A 3 B 3 is can be obtained, put in R 1 R 2. So, it goes on, and it turns out it would have taken, you can see that each operation each of this, like given A, B and C, A 1, B 1, C 1, it takes 3 cycles. So, you may expect that I have to take 15 cycles for 5 data sets, but it will take less. Okay. For large data set, you just take n rather than 3 times n. Okay. So, that is what is pipelining. Okay. Any questions on this? Yeah.
In vectorization, why it is limited to 20 times speed? According to this lecture, it may be as no data possible as much speed.
No, but registers. How many registers do you have in CPU?
Lack of register in the CPU.
That is the memory inside CPU is limited. You can't put few all of array inside CPU. Okay. That is a good question, but that's what it is. Any other question?
Sir, so registers store the addresses of the RAM data.
No. Register have address as well as the content of the data. When I add number, I need the number inside the CPU. So, if I am doing, imagine I am doing 5 plus 6. So, of course, 5 is stored somewhere in memory. So, memory is like this. So, 5 is stored here and 6 is stored here. So, indeed CPU sends the address. So, get the next number. So, this address is sent, and then 5 will come by this bus wire, and then they will fetch 6. So, 6 will also come, and then this 5 and 6 are sitting in registers, and then we say add. So, 11 will be written in another register, we saw that. Okay. So, this is my answer, and this addition will involve some circuit operations. Okay. I mean you know how things are done, no? I mean 1 0 1, this 5 and 6 is 1 1 0. So, first time you add these 2 bits and then this bits and there is a carry over. So, this circuit is done, it will not be done in one shot because carry over is required. So, I think is done, and these are specialized hardwares which will do this. Okay. So, data is there inside the CPU, inside the processor. Okay. Any other question?
Sir, and you said to avoid if, so what is the alternative? So, what do we use to avoid?
Actually, in general, if can be avoided. When I am doing PD solver, okay, partial differential equation solver, then I have an array. So, you should put everything in array. My velocity field u x, u y, u z, and I just say, well, u x equal u x at time t plus delta t is u x at t plus delta t times RHS at t. So, it turns out you do not need if is in I have full data set, I just push it. If is required in the boundary conditions, okay, at the edge. So, that is where if I am at the edge, then do this, but you should write clever code cleverly, so that you include edge also in this. So, you have to be clever in handling those stuff. So, your array can be slightly bigger, but that does not harm you. Okay. So, avoid if. If means you will be only that time you will only one operation, and that too it will be slow. So, you should avoid if. It is avoidable, it is not that, you just have to be clever. Okay.
But sir,
Yeah.
inside function we can define if and then we can put that.
That function will become slow then. Okay. You can say in the main code, if this then that function. So, if there are two different kind of blocks, then you can use if, but try to avoid if at all cost if you can. Okay. So, function will slow down if you any code, if you put if inside, is going to slow things.
No, I am just doing it. I am putting if inside the function, and then we can.
Yeah, that function will slow down, no, inside the function. So, function is also a code block. If I put if here, then I will be making a jump. In fact, function you should avoid if. In the main code you can have if. The main code is big blocks. So, you can say that, well, I mean the boss can say this person will do this, this person will do this, if something happens this person will go. So, you should avoid, for big chunk you can use if, for a small chunk you should not use if. Okay. And I think it comes by experience, it does not happen all of a sudden, but it happens by experience. So, we discussed presently one single core, well basically single unit, but it turns out modern processors have many cores. Okay. In your own laptop you would have quad core, nowadays is octa core, 8 cores are coming, and the best machines right now have 128 cores. Okay. Is available now. So, let us look at some real HPC processors. Okay. I can't cover many of them, but I will cover only 2 of them. One of them is not HPC, but is a very interesting design. So, I will give you some, I will have some discussion on that.